Matched filters are optimum filters for the detection of pulse signals in noise. The matched filter is the optimal linear filter for maximizing the signal-to-noise ratio in the presence of additive stochastic noise. For a system response function Gt and an input signal Ft, the following integral calculates the output signal shape in the time domain. The equation is the standard convolution integral. The animation shows a square pulse sent into a system with a simple RC low-pass filter. The output is a function of the capacitive reactance. The lower plot shows graphically that using the time domain convolution we can calculate the familiar exponential rise and fall for the output. The red curve is the impulse response of the RC filter, shown in the time domain. The green signal is the square wave input signal. The gray area is the overlap, and the value of the overlap is plotted instant by instant on the bottom curve. The bottom red curve is, therefore, the overlap integral, but it is also the signal shape for a square pulse propagating through a simple RC low-pass filter. It shows the familiar form of a rectangle pulse distorted by this low-pass filter. But the low-pass filter is not yet a matched filter. However, it would have already filtered out the noise components with higher frequencies. What is a matched filter, and why does anyone care? To answer, we need to establish a few facts. There must exist an optimum filter shape for maximizing the signal-to-noise ratio and thus sensitivity of the receiver. The bandwidth of the filter should be as low as possible to reduce the introduced noise. In contrast, it is essential to have sufficient bandwidth to capture all energy components of the signal being searched for. The optimum filter shape can be calculated for a particular input pulse shape and is different for each type of pulse. Obviously, fast pulses need a higher bandwidth filter than slow pulses. In the time domain, the impulse response of the filter should exactly match the shape of the incoming data. These filters are called matched filter and are used in radar signal processors or in radar receivers to detect the shape of the transmitted signal in the received signal. The additive white Gaussian noise channel, abbreviated AWGN channel, is a basic noise model used in information theory. An AWGN channel adds white Gaussian noise to the signal that passes through it. It is a theoretical equivalent circuit diagram for all noise sources that are added to the signal during transmission. Here we use it to visualize the input signal mix at the receiver input. The observer uses a linear time invariant filter with impulse response h, t, and samples the filter output y as a function of time t. Output pulse shapes can be evaluated in the time or frequency domain, both are equivalent. A filter whose impulse response is a delayed time reversed version of a signal st is called matched to st. A receiver that is equipped with such filters is called a matched receiver. Matched filter responses are characterized fully by either their frequency response, h, omega, or their impulse response ht. However, they are usually specified by a variety of parameters. The filter needs to detect the precise spectrum used in the transmitted signal. It should not miss any part of the spectrum. However, it should also not allow any extra frequencies as they can increase the amount of noise, which is always broadband. The classic radar transmission pulse can be represented by the symbol s, which is a function of time, t. Similarly, the symbol n represents white Gaussian noise, which is also a function of time. With radar, the additive white Gaussian noise channel includes the free space path losses, modifications during reflection and diffraction at an object, and the return path. The signal at the receiver input is represented by r as a function of time, t, which is the sum of the amplitudes of both signals. The matched filter's task is to separate this merged signal at the input and provide the result as function y. The operation of matched filters is the same as correlating a signal with a copy of itself. This process is also called autocorrelation. Matched filter impulse response is a flipped-in-place version of the signal. The correlation means the projecting of one signal onto another. It is a means of measuring how much of the second signal is present in the first. This can be used to detect the presence of known signals as components of more complicated signals. The red rectangle is the impulse response, in the time domain, of an appropriate matched filter for a rectangle signal. Green is the rectangle input pulse, also in the time domain. As before, the gray area is the convolution or overlap. The bottom plot is the instant-by-instant value of the overlap and thus gives the output pulse shape. The output of a matched filter for rectangle pulses is always a triangular pulse. But which output signal would make an arbitrary, but known, signal? For example, the rectangle with a sawn-off corner. I didn't want to believe it. However, during the creation of the animation, I counted the number of pixels in the gray overlap area frame by frame, transferred it to an Excel file, and displayed the data as a diagram. The result was an exact isosceles triangle. Here you can also see that the passband characteristic of the matched filter must be a time-reversed copy of the signal we want to detect. This counting process can also be carried out using mathematical equations. The output voltage of the matched filter was the function y, t, which had the shape of a triangle in the previous animation. The individual points of this output function were the current area of overlap between the two input functions. The area under a function curve is calculated using an integral. The limits of the integral range from 0 to time t. Note that the functions are multiplied. This is important, for example, for the matched filter for a Barker code. Here, some areas have a negative sign and are therefore subtracted from the overall result. It can also happen that both areas have a negative sign, which then leads to a positive value again. The evaluation circuit, or the digital evaluation function, compares the phases in the Barker code. The result is not only a very good signal-to-noise ratio but also pulse compression. The Barker code is a known waveform. Despite the fact that possible Doppler frequencies influence the frequencies of the entire echo signal, the phase difference in the partial pulses is retained. However, if the matched filter must be realized via the frequency response, then Doppler frequencies lead to a mismatch of the matched filter. In some cases, there can be multiple Doppler frequencies, such as when propellers are rotating. If an object is geometrically large, it can cause an enlargement in time of the echo signal. Additionally, harmonics may occur during reflection at transition layers with nonlinear characteristics. So, we must say that the waveform of the backscattering is unknown. The well-known analog-coded signal is in this example a linear frequency modulated signal and its matched filter. All components are filtered and delayed to the falling edge of the pulse at least. Using of matched filter presupposes that the waveform of the wanted signal is known. In this form, the matched filter is only optimal for fixed targets. But radar is looking for moving targets and their waveform is unknown. Well, you know the transmitted signal, but the backscattered signal is modified in many parameters. All these changes contain detailed information about the target and its movement, in speed and direction. Assuming a high Doppler frequency overlaid to this linear frequency modulated waveform will shift the whole waveform left or right in this diagram. In this case, one or more stages of the matched filter don't work. While the waiting stages get the wrong part of the signal, they have an improper value, and the output signal is fairly decreased and deformed then. The slide shows a common solution. There are a wide number of matched filters, each representing another expected waveform changed by backscattering. An electronic switch decides the greatest of. Now the signal with the best signal-to-noise ratio can pass this switch. Output signals of all other filters have a higher noise level and must be switched off. The number of the switching positions is also used as a measurement result for the Doppler frequency. Of course, this principle is too complex for discrete wiring. Remember, all these individually matched filter blocks MF1 to MFN contain the whole diagram of the previous slide but are optimized for slightly other frequencies. Therefore, this solution is reserved for digital signal processing. These routines are calculated using target models and implemented as standard in radar software. One radar software manufacturer, Cambridge Pixel in the United Kingdom, also sponsors the Radartutorial. I hope you enjoyed this video. You may find the internet Radartutorial useful. It has a vast collection of radar set data. Thank you for your attention.